Billions of years ago, something grew so large in space that today it defies everything we thought was possible. Imagine a black hole so giant that our entire solar system would fit inside it, with room to spare. Scientists have discovered space monsters with mass equal to 66 billion suns combined. It's so heavy that if you put it on a scale, it would weigh more than entire galaxies. But here comes the scariest part. This giant is still growing, devouring millions of stars per year like they were grains of sand. How can something get so absurdly big? And the most disturbing question, is there a limit to how large these things can get, or will they keep growing forever until they swallow everything that exists? Subscribe to the channel. Leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. What makes something in space so powerful that even light cannot escape? This question leads us to one of the strangest and most interesting things in the entire universe: the black hole. A black hole is not a hole in the normal sense. It is a place in space where an enormous amount of material has been squeezed all the way down into a very small area. Imagine if you could keep pressing the Earth smaller and smaller until all of its weight fit into something even smaller than a marble. What you would end up with is extremely heavy and packed so tightly that nothing, not even light, can get out. Every object in the universe pulls other things toward it. This pull is called gravity. The bigger and heavier something is, the stronger its gravity. The Sun has much more gravity than the Earth, so it keeps all the planets moving in large circles around it. A black hole has even more gravity than that. In fact, its gravity is so strong that it can trap anything that comes too close. Once something goes past a certain point, it can never escape. This special point around a black hole is called the event horizon. The event horizon is not a thing you can touch. It is just an invisible boundary. If you crossed it, you would not be able to turn back, no matter how hard you tried. Light is the fastest thing we know, yet even light cannot escape this boundary. That is why black holes seem invisible or completely black. Our eyes cannot see what is inside because no light or information can come back out to us. For a long time, people only guessed about black holes. The idea first came from thinking about what happens when things get very, very heavy and squashed into a tiny space. Later, scientists did equations and realized that the laws of physics really allowed this to happen. These discoveries showed that black holes could be real things in the universe. After a while, using special telescopes, scientists began finding places in space where a lot of strange things were happening. They now believe there are many black holes out in space. But if black holes are invisible, how do we know they exist? The answer is that we cannot see them directly, but we can see how they change everything around them. When a black hole pulls in nearby gas and dust, all of this material starts to quickly spin in circles around the black hole. It forms something called an accretion disk. This spinning gas moves so fast that it gets very hot, often millions of degrees. When things are that hot, they give off energy and light, including special kinds of light like X-rays. Telescopes on Earth and in space can pick up these X-rays. So, when we see a bright spot of X-rays in the sky and nothing else explains it, we think there might be a black hole there. Black holes come in different sizes. Some are only a little heavier than our Sun. These small ones are called stellar black holes. Others are millions or billions of times heavier than the Sun. These biggest ones are called supermassive black holes. The supermassive black holes are usually found in the middle of galaxies. A galaxy is a giant group of stars, dust, and gas. Our own galaxy, called the Milky Way, has a supermassive black hole at its center. Even though it is very heavy, it is far enough away that it does not hurt us on Earth. Scientists are very interested in black holes because their pull is so strong that it changes how everything nearby moves. If a star gets too close to a black hole, the gravity can pull the star apart. The pieces of that star swirl into the black hole and add to its weight. Sometimes, black holes swallow so much gas, dust, or even whole stars that they keep growing bigger and bigger. Learning about black holes helps us understand basic rules about how the universe works. For example, the idea that nothing can get out of a black hole, not even light, tells us a lot about gravity. It teaches us that when things become heavy enough and squeezed in a small enough area, the force of gravity is unlike anything we see in our everyday lives. Not everything can become a black hole. Most things in the universe are not heavy enough or dense enough. To create a black hole, something must have a lot of material packed tightly together. That is why most black holes start from very big stars. When these huge stars run out of fuel, the pressure that held them up disappears. Gravity takes over, squeezing all of the star's matter into a very small space. What is left is a black hole. Many years ago, scientists only knew about black holes in theory. Now, with better telescopes and computers, they study the areas near black holes much more closely. They watch the hottest gas moving at great speeds. They check how the paths of stars and other objects bend or change as they move past invisible spots in space. With each new study, they learn more about black holes and the strange things they do. Black holes change the way people think about space and time. Near a black hole, even time moves differently. Time seems to slow down as you get closer to a black hole's event horizon. This sounds very strange, but it comes from the equations that scientists use to study how gravity works. Black holes show us that the universe can behave in ways that are hard to imagine. Sometimes, black holes are found by watching stars that move in odd ways. If a star in the sky seems to go around an invisible spot and nothing else is there to see, a black hole might be pulling it. Other times, black holes are found by the hot, bright energy that comes from their accretion disks. More often now, scientists also look for tiny shaking signals called gravitational waves. These waves happen when two black holes crash into each other and make one bigger black hole. These waves travel across the universe and can be picked up by very careful experiments on Earth. Over the years, scientists have also learned that black holes come in a range of weights. The smallest ones, formed from the collapse of stars, may be only a few times heavier than the Sun. These are called stellar mass black holes. Some black holes are thousands or even millions of times heavier. These are called intermediate black holes and supermassive black holes. Supermassive black holes are puzzling. They are so heavy that it is still a mystery how they got that way. Did they start small and slowly grow, pulling in gas and stars for billions of years? Or did they already start off big, formed when the universe itself was very young and full of thick clouds of gas? Scientists do not have a full answer yet, but they keep looking for more clues. One of the most interesting things about supermassive black holes is that they can control whole galaxies. Their strong pull affects how stars move many light years away. Galaxies themselves seem to grow around these giant black holes, not the other way around. This means that black holes, even though they are small compared to the size of the galaxy, may be very important for shaping the universe. Even though black holes are known for pulling everything in, not all parts of a black hole act the same. Outside the event horizon, things can move around the black hole without falling in. But once anything goes past the event horizon, it is lost, and we cannot get information about what happens inside. Black holes are some of the most mysterious objects in all of science. Their gravity is the strongest force we know. at least outside the center of atoms. They challenge the rules we have for how light and matter behave. The study of black holes has helped people make many new discoveries about space, stars, and even the history of the universe. The more scientists look at black holes, the more surprises they find. For example, as material falls toward a black hole, it does not just disappear quietly. Instead, the process can make some of the brightest lights in all of space. These lights, called quasars, can shine brighter than whole galaxies. A quasar acts like a lighthouse, showing us where a supermassive black hole is eating material and shining with its energy. Black holes can also be hard to find because, without anything nearby to eat, they do not give off light or energy. These are called quiet or dormant black holes. They are invisible unless a passing star or cloud of gas gives them something to pull in. Because black holes are so strange and hard to see, they make scientists want to keep asking questions. Why do some black holes never get very big, while others become supermassive? Are there even bigger black holes out there that we have not found yet? Is there a maximum size a black hole can reach? Can black holes change the way the whole universe acts over time? These questions do not have full answers yet. As scientists build better and better tools, they hope to find more black holes and learn more about how they work. Special telescopes that can pick up X-rays, radio waves, and even gravitational waves all help us find new information. Computers help by running models and simulations, letting scientists test their ideas and compare them to what we see in space. Black holes are strange, powerful, and important. Even though they are invisible, we can still learn a lot from what happens around them. Every time something new is measured, it changes what we know about not just black holes, but about the whole universe. The story of black holes is not just about things disappearing. It is about learning where stars come from, how galaxies grow, and what the rules of the universe really are. Understanding what a black hole truly is means looking at some of the biggest questions in science. Why does gravity become so strong in some places? What happens to things that fall in and never come back? Can we ever know what is inside a black hole, or is it lost to us forever? As we keep studying, each answer brings new puzzles. A black hole is nature's way of showing how the laws of physics can bend and change when things get extreme. With every discovery, black holes continue to be some of the most mysterious and exciting things in all of space. They make us keep looking up and asking new questions about what happens out there, far beyond our own planet. There are many kinds of objects in the universe, but black holes hold a special place. They stretch our knowledge to its limits, making us wonder just how much more there is to learn. The first step to understanding black holes is remembering that it is not just about darkness and disappearing things. It is about the power of gravity, the movement of stars, and the very shape of space itself. Black holes remind us that space is full of mysteries, and every mystery is a chance to discover something new. As we keep exploring, black holes will always challenge us to look deeper and think harder, showing us that the universe is bigger, stranger, and more amazing than we ever thought possible. The way black holes are made is one of the most strange and important parts of their story. To understand how a black hole begins, it is good to start with stars, because most black holes come from the life and death of very large stars. Stars are huge balls made mostly of burning gas. Every star shines because it burns fuel inside, making energy and light. This burning is not fire like on Earth, but a strong kind of reaction deep inside the star. The fuel for stars is usually hydrogen. This hydrogen is turned into helium, and this makes the star shine and keeps it hot for a very long time. A star keeps burning its fuel, making light and heat for millions or even billions of years. The bigger a star is, the faster it burns its fuel. Very large stars use their fuel much more quickly than small ones. When a huge star has burned almost all its fuel, something important happens. It cannot make enough energy to push outward against its own gravity. Gravity is the force that always tries to pull everything together. For the star, gravity is always trying to pull all its material inward, while the burning inside tries to push everything out. As long as a star has enough fuel, the inside and outside forces balance each other. But when the star's fuel is almost finished, there is nothing left to stop gravity from taking over. The star starts to collapse. This means that the whole star begins to fall in on itself, getting smaller and smaller. The outer layers of the star might blow away into space, but the core, the very center, gets squeezed tighter and tighter. For some stars, this collapse stops before they become black holes. If the star is not very large, it might turn into a white dwarf or a neutron star. A white dwarf is a very small, hot core that cools down over billions of years. A neutron star is even smaller and heavier, squeezed so much that the atoms are changed. But if a star is much heavier than our Sun, gravity keeps pushing, and the core keeps shrinking until it gets so small and heavy that a black hole is formed. There is no force in nature that can stop this collapse when the star is massive enough. The entire core gets crushed into a tiny space called a singularity, where its weight becomes nearly endless and the pull of gravity is the strongest known. The place around this tiny point where nothing can escape is called the event horizon. The event horizon forms because the gravity at this spot is so strong that even light cannot get away. Anything that passes too close to the new black hole cannot turn back. This is how a black hole is born in space. Sometimes the birth of a black hole happens with a bright explosion called a supernova. When very large stars die, their final collapse can push their outer parts outward, making a burst of light that is brighter than almost anything else in the sky. After the supernova, the center that is left behind can be the black hole. Other times, the star does not make a bright supernova. Instead, it just collapses quietly and hides as a black hole. Most of the stars in the universe are not big enough to become black holes. The Sun, for example, is not heavy enough, and when its fuel runs out, it will become a white dwarf. A star usually has to be at least about 3 times as heavy as our Sun, or even more, to turn into a black hole at the end of its life. There are other ways that black holes can form too. In space, there are many places where stars and black holes come close together. Sometimes, 2 stars that orbit each other can both become black holes, or one might turn into a black hole first. If 2 black holes end up close enough, they can circle around each other and finally crash together. When this happens, they join to make a new, bigger black hole. Scientists have seen signals from space called gravitational waves that show this process really happens. Gravitational waves are small ripples that travel through space when heavy objects move very fast or join together. Detecting these waves is one way that scientists know black holes are growing by joining with others. Sometimes black holes can also form in groups of stars. In these places, stars are packed very close together. If 2 or more very massive stars form close to each other, their deaths can lead to the creation of multiple black holes, which might later combine. This process can make black holes that are heavier than those formed by just one star. The story of forming black holes is not only a story about dying stars, it is also a story about the whole universe. When the universe was very young, right after the Big Bang, the conditions were different from now. The first stars that formed were much bigger than most stars today. These giant early stars could have ended their lives by making the first black holes. Scientists think that some supermassive black holes, the kind that sit in the center of galaxies, may have begun as these early black holes and grew larger over billions of years. Scientists are always looking for clues in space to find which stars have died and become black holes. It is hard because once a black hole forms, it disappears from view. It is only the things happening around the black hole, like leftover gas, spinning stars, or even flashes of light from supernovas, that can give a sign that a black hole has appeared. It is not only stars that can make black holes. Some scientists think that smaller black holes could have formed right after the Big Bang, when the universe was still very crowded and hot. If parts of space in those early times were packed enough, a black hole could have formed there, not from a star, but directly from the dense material of the early universe. These are called primordial black holes. Scientists are still looking for proof that any of these exist, but if they do, they would have formed in the first seconds after the universe began. When a black hole is first made, it does not always stay the same size. Many black holes keep growing after they form. They pull in gas, dust, and anything that comes close. Sometimes, a black hole might eat an entire star that gets drawn too near. Other times, it grows slowly, collecting small bits of gas over millions of years. When two black holes come together, the new black hole is heavier than both of the old ones. Black holes change their part of space in many ways as they grow. The gravity from a black hole changes the paths of stars and gas clouds nearby. It can even change whole star clusters or the centers of galaxies. As black holes pull in material, they often create bright waves of energy. This helps scientists find them, even when the black hole itself remains hidden. The growth of a black hole depends on how much material is close by to eat. In the middle of some galaxies, there is lots of gas and dust, so black holes there can grow very quickly. In other parts of space, there might not be much for the black hole to pull in, so it stays smaller for a much longer time. When two black holes join together, they can make a big burst of energy. Scientists with special machines called interferometers can feel these bursts as small shaking waves in space-time. This has helped prove that black holes really do merge and get bigger. With each new way black holes can grow or form, scientists learn more about the universe. They find out that black holes are not just dead ends for old stars. They are also places where enormous amounts of matter and even bright energy are concentrated in space. Every time a star dies and makes a black hole, the story of that star is not over. The black hole can have a big effect on its surroundings. It can keep swallowing things, gaining weight. Over millions or billions of years, what started as the death of one single star can grow into something much bigger and more important. The size of the black hole that forms at first depends on how big the original star was. The bigger the star, the bigger the black hole. But the story does not stop there, because after formation, black holes can merge and feed, becoming even heavier. Not all black holes come from stars. In some situations, two neutron stars, these are very tight, small cores left after medium-sized stars die, can crash into each other. When this happens, the collision is so powerful that a black hole is made out of the two joined objects. Scientists have watched this process by seeing both a flash of light and feeling gravitational waves at the same time. The life cycle of stars and the making of black holes is a large part of how the universe changes with time. As old stars die and new black holes are born, the galaxies and clusters of stars change shape. Black holes help spread out elements made inside stars, and sometimes their bursts of energy can even help create new stars in the clouds around them. Most of the black holes seen by scientists today are the kind formed from stars dying. They are only a little bit heavier than the star was before, usually a few times the mass of the Sun. These are called stellar black holes. Most galaxies might have millions of these hidden in their dark spaces. Some black holes form in strange ways, not only from stars, but from the joining of many smaller black holes. If enough black holes collect in one place, gravity can pull them together into much bigger ones. This may be one way that some of the largest black holes have grown to be so massive. Black holes can sometimes be found inside very large groups of stars called globular clusters. In these clusters, hundreds of thousands or even millions of stars are packed close together. Some of these clusters could have made their own black holes long ago when the biggest stars died out, and now those black holes may still be hiding inside. Black holes also tell us about the end of a star's life. For a star, burning up its fuel is the last act before becoming something new. When that last bit of fuel is used, gravity brings everything together and the core collapses under its own weight. In the most massive stars, nothing can stop the collapse and a black hole forms, hiding inside its event horizon. The beginning of a black hole marks a new chapter in space. It may seem like an ending, but it is really the start of something bigger. These black holes shape their surroundings, make energy, and sometimes grow into the most powerful objects in the whole universe. Science keeps searching for the exact rules about when a star will become a black hole and when it will become something else like a neutron star. It looks at the weight of the star, the way it loses its gas, and how the very center of the star is squeezed by gravity. There is still a lot to learn about how black holes begin and exactly how different kinds are made. Some scientists think there may be types of black holes that we have never seen yet, formed from things other than dying stars or merging black holes. There could be hidden kinds left over from the very beginning of the universe. With every new discovery, we get closer to understanding the story of how black holes are made. The birth of a black hole is a powerful event, changing not only one star but helping build galaxies and even changing the course of matter and energy in the universe. The end of a star, the merging of dead stars, or the joining of two black holes can all give rise to a new black hole. In all these ways, gravity collects matter so tightly that nothing can escape once it has formed. This is how black holes first appear, and then start to affect the space around them, shaping the universe in ways that we are only beginning to figure out. Black holes push the laws of gravity further than anything else in the universe. Gravity shapes how they start, how they grow, and what happens near them. Gravity is not just what pulls things down on Earth. It is a force that exists between every object with mass anywhere in space. Every person, animal, rock, tree, planet, and star has gravity, even though we usually do not feel its effects if something is small. The larger and heavier something is, the stronger its gravity becomes. The sun's gravity keeps the planets in their places, making them move in circles around it and holding the whole solar system together. The moon's gravity gently pulls the water on Earth, making tides. Everything that has weight pulls on everything else all the time, but this pull is very tiny unless one or both objects are big. Black holes show us gravity at its strongest. When a heavy star runs out of energy and collapses, gravity squeezes all its matter into a tiny space. This tiny space holds the full weight of the star, so gravity becomes so extreme that nothing can stop it. The black hole's pull becomes endless, strong enough to trap everything near it. Around each black hole is a zone with a special rule. Once anything crosses into this zone, it can never return. This zone is called the event horizon. The pull inside the event horizon is so strong that it crushes anything trying to escape. If you could stand just outside this edge, you would feel gravity much stronger than anywhere else. But it is not possible for any person or object to survive at this distance. Gravity near a black hole is not just a little stronger. It is so much stronger that it changes how space and time behave. Space near a black hole bends inward. The closer you get, the more space seems to fold. Even time slows down when you move near a black hole. If a clock was set close to the event horizon, it would tick much more slowly than a clock far away from the black hole. This is not something you can see with your eyes, but scientists have found proof that this happens by studying light and other signals near black holes. The event horizon is not a wall or a surface you could touch. It is simply a border in space. Light moves unbelievably fast, faster than anything else in the universe, but even light cannot leave once it goes inside the event horizon. That is why no light reaches us from inside a black hole, making it always dark. Black holes show the strongest kind of gravity known. Gravity keeps growing the closer you get. For a small black hole, the event horizon is tight, pulled in close to the center. For very large black holes, the event horizon is farther out, but the pull is still the same. Nothing can get out. Gravity outside a black hole is more familiar. Far away, things move as they would near any other heavy object. Stars, gas clouds, and even other black holes can orbit a black hole, just like planets move around a star. These orbits are not always peaceful. If these things get too close, gravity can pull them apart, stretch them, or gulp them down to become part of the black hole's mass. When something falls toward a black hole, gravity pulls it faster and faster. As it gets close, the speed and energy increase so much that the thing can break apart or get very hot before it finally disappears past the event horizon. This action creates bright light, strong X-rays, or powerful jets of energy. Scientists use special telescopes to watch these signals because they tell us where black holes are and how strong their gravity is. The gravity of a black hole can shape the space around it in many ways. Gas and dust close to the black hole swirl in circles, moving quickly, forming a hot, spinning disk. This disk is called an accretion disk. Its bright light comes from the heat made by friction as the gas and dust spiral in faster and faster. Nothing in space gets so hot so quickly as matter caught near a black hole. By seeing how fast the gas spins, scientists can measure the gravity, and from the gravity, they learn how heavy the black hole is. Stars that come too close to a black hole can be ripped apart. Their pieces swirl into the accretion disk, making flashes of light and energy. These events are called tidal disruption events. They are powerful signs of gravity at work. Even things that do not fall in or get too close are changed by the black hole's gravity. Their paths bend as they travel near, sometimes flying around the black hole or being slung far off into space. The black hole's gravity acts as a powerful guide, steering objects as they move through space. Gravity can also hold on to whole clusters of stars, keeping them held tight around the black hole for millions or billions of years. The power of a black hole's gravity attracts not only gas and dust, but other black holes as well. When two black holes drift close, their gravity makes them spiral toward each other. They move faster and closer until, finally, they join. As they merge, they make ripples through space called gravitational waves. These are not light or sound, but gentle stretching and squeezing of space itself, moving outward at the speed of light. Scientists have learned to measure these small waves using very special equipment here on Earth. Gravity is not just a pull. It stretches, bends, and changes space-time. Space-time is the way scientists describe how space and time work together. Near a black hole, gravity is so powerful It bends this space-time more than anywhere else. Watching how space-time bends tells scientists where black holes are, how big they are, and how they affect the things around them. When you look at a galaxy, you are seeing millions or billions of stars. Most galaxies have black holes in their centers. The gravity from these black holes helps keep the galaxy together. Some galaxies even have more than one black hole, and if these black holes join together, the new black hole gets bigger. Gravity keeps galaxies the shape they are. Galaxies are full of stars, gas, and dust moving under the pull of gravity. Black holes, especially the largest supermassive black holes, are part of the reason galaxies stay bound together. These giant black holes help hold stars close, even though they all move in vast orbits around the center. The extreme gravity of black holes can also shoot out beams or jets of energy. These jets come from just outside the event horizon, where twisting magnetic fields and energy build up as matter gets spun around quickly. The jets and bursts are so strong they can travel far beyond their galaxy. Gravity has rules. The force gets weaker as you move farther from the black hole. If you are very far away, you will not feel its pull more than being near any other star or planet. If your path brings you close, gravity's pull becomes stronger and stronger. The point of no return is always at the event horizon. That is the last chance to turn back. Past that, everything is captured by the black hole forever. Scientists use many kinds of measurements to see how gravity is working around black holes. They watch the orbits of stars, the movement of gas clouds, the way light bends, and the bursts of energy produced by falling matter. All these signs are used to measure the power and nature of gravity near black holes. Black holes help scientists test some of the deepest ideas about how the universe works. The rules of gravity that work in our everyday lives become different and more complex near a black hole. Even time and space behave differently. By studying black holes, scientists learn new things about the basic laws that control everything in the universe. Black holes do not pull everything in right away. Only things that get very close are trapped. Farther away, objects can orbit safely for a very long time. Planets, stars, and even light from far away can pass close and just be bent by gravity without falling in. The black hole's pull only becomes unstoppable at the event horizon. While black holes have the strongest gravity, their size is very small compared to the galaxies they are in. Even the biggest, supermassive black holes are tiny points at the centers of huge galaxies. The gravity is only that powerful nearby, not throughout the whole galaxy. Sometimes black holes pass through clouds of gas. Their gravity pulls in the gas, which heats up and glows before disappearing inside. If a star is caught, the same thing happens. The gravity tears it apart, and the matter falls in, adding more weight to the black hole. Solving the puzzles of gravity is one of the oldest and hardest parts of science. Long ago, people noticed that things fall on Earth and that planets moved in the sky. Over hundreds of years, scientists have built up the rules to explain these motions. With black holes, the rules lead to new questions because gravity becomes so strong it changes all the usual patterns of movement, time, and light. Black holes show us gravity's fiercest power. Their existence proves that gravity can crush stars, trap light, bend space, and even make time slow down. The study of these objects continues to stretch the edges of what people know, letting scientists look for new answers. Gravity is also responsible for the growth of black holes. The more the black hole eats, the heavier it gets, and the stronger its gravity becomes. Over millions or billions of years, this cycle lets some black holes, especially those in the centers of galaxies, become very large. Some have swallowed enough matter to reach millions or billions of times the mass of the Sun. The way black holes shape their surroundings always goes back to gravity. They bend the paths of stars, shape gas clouds, light up energy jets, and even create ripples through space. Their gravity holds together the hearts of galaxies and causes new black hole mergers. There are many kinds of black holes, but they all have the same rule. Once something passes inside the event horizon, gravity will never let it leave. This simple but powerful truth is the reason black holes are so mysterious and important in the study of space. Because the pull of gravity gets stronger as things get closer, time even acts differently. If you watched a flashlight fall toward a black hole, its light would seem to slow down and get dimmer as it neared the event horizon. If you could watch from far away, you would never see the flashlight cross the border. The light's speed would keep slowing and fading until it was gone. Gravity is also why black holes can trap even light. Light always travels at the same speed, but inside the event horizon the space is curved in such a way that all paths lead inward and none outward. Not even a beam of light can escape the strong pull. Scientists sometimes use big computers to run models of how gravity acts near black holes. These simulations help them predict how gas will move, where energy will come from, how jets form, and how mergers will shake space with gravitational waves. Gravity's effects near a black hole are so great that they allow scientists to test their theories about how the universe works at its most basic level. Tests near black holes have even helped us confirm that the rules of gravity also explain what happens in the strongest, strangest places. Even after so many discoveries, scientists are still looking for new surprises in the rules of gravity. Black holes let them study space, time, and matter in the most extreme places known. Some hope to find evidence for new kinds of physics by watching black holes closely, using powerful telescopes and studying how gravity works at the very edges of what we can measure. The role of gravity does not stop with the black hole itself. It stretches out to shape galaxies, help create new stars, and even spread heavy elements that will someday form new planets and suns. Black holes are not just destroyers. Their great gravity can also help build and change the universe at every scale. Today, scientists use gravity maps to spot signs of invisible black holes. When a big invisible object makes stars move or light bend, this can be a clue that a black hole is there. Gravity is always acting everywhere in the universe, and black holes are its greatest showcase. Through black holes, gravity changes space, shapes new objects, breaks apart old ones, and makes the universe as full of mystery and wonder as it is. Exploring black holes helps everyone see that even the most basic forces in nature can lead to endless questions and discoveries. The force of gravity, strongest near these mysterious places, still shapes everything on the largest and smallest scales. The story of gravity's power and of black holes themselves goes on as we look deeper into space, searching for even more answers to the universe's secrets. As scientists have watched how gravity shapes the universe, they have learned there are many types of black holes. Some are small, created when single, large stars reach the end of their lives. Others are much bigger, created when many stars collapse, or when black holes join together. But there is a type of black hole that stands out above all the rest for its enormous size and power: the supermassive black hole. Supermassive black holes are the largest kind that scientists have found so far. They are not only a little heavier than regular black holes. They can be millions or even billions of times heavier than our Sun. These giant black holes are found almost always at the center of galaxies. A galaxy is a huge collection of stars, gas, dust, and dark matter held together by gravity. Every galaxy that scientists have looked at closely enough seems to have a supermassive black hole sitting right in the middle. The discovery of supermassive black holes did not happen in one single moment. For many years, scientists saw strange things happening at the hearts of distant galaxies. Some galaxies shined much brighter in their centers than others, as if something there was giving off enormous amounts of light and energy. Using many types of telescopes, scientists began to see that this light was coming from regions smaller than a galaxy, but much brighter than billions of stars put together. They realized that only something with extremely strong gravity and the ability to swallow enormous amounts of gas and stars could make this much energy, a supermassive black hole. Supermassive black holes are so heavy because of how much matter they have gathered over their lives. Scientists believe that early in the history of the universe, galaxies were full of thick clouds of gas. In these crowded places, black holes could grow much faster by pulling in huge amounts of this gas, as well as dust and even whole stars. Some supermassive black holes might have also grown by merging with other black holes, each time becoming bigger. The process of growing takes millions or even billions of years. At the beginning, the black hole might only be a few times as heavy as our Sun. But after a long time of pulling in more and more material, and after joining with other black holes, the mass keeps increasing. When scientists look at very distant galaxies, they are actually looking back in time because light takes a long time to travel across space. They have seen some supermassive black holes that were already huge when the universe was much younger, showing that some black holes grew very large very quickly. The way that supermassive black holes affect the centers of galaxies is very powerful. Their gravity shapes how gas and stars move. In many cases, stars at the center of a galaxy are seen spinning very fast around an invisible, heavy object. By measuring the speeds and paths of these stars, scientists can tell how much mass is sitting in the center, even if they cannot see the black hole itself. The faster the stars go, the more massive the black hole has to be. The material falling toward a supermassive black hole does not just disappear quietly. As it gets close, the gas and dust swirl around in a flat spinning disk called an accretion disk. Friction makes the material in this disk very hot, sometimes getting so hot that it glows brightly in X-rays and other types of light. This energy can be seen from far away by powerful telescopes, even all the way from a different galaxy. In some cases, supermassive black holes are so active they shine brighter than the billions of stars in the galaxy around them. When a supermassive black hole is eating a lot of gas and giving off huge amounts of energy, scientists call this state a quasar. Quasars are some of the brightest things ever discovered in space. They are so bright that they can be seen from billions of light years away, even when their home galaxy is very hard to see. The light from the region near the black hole travels across the universe and gives us a way to find these powerful objects, even though the black hole itself cannot be seen. Supermassive black holes do not only affect things right next to them. Their strong gravity helps control the whole galaxy. They can change how galaxies grow and even how stars are born. When material is falling into a supermassive black hole, it can make powerful jets of particles and energy shoot out from near the event horizon. These jets can push gas far away from the center, heat up the surroundings, and stop new stars from forming close by. Not all supermassive black holes are active. Some are very quiet. When there is little or no gas close to them, they do not shine or make bright X-rays. These quiet black holes are hard to find, but their gravity still shapes the movement of stars and gas near the galaxy center. Scientists discover them by seeing how things move around something heavy that cannot be seen any other way. The supermassive black hole closest to us is in the center of our own galaxy, the Milky Way. This black hole is called Sagittarius, a star. It is about 4 million times the mass of the Sun. Although this seems very big, many other galaxies have black holes that are much larger. Some, like the one known as TON 618, are among the most massive objects ever measured. These supermassive black holes reach sizes that are hard to imagine, packing billions of times the mass of the Sun into a volume smaller than the solar system. Scientists have many questions about supermassive black holes. One is how they became so big in the first place. Some believe that the very first stars in the universe were much larger than today's stars, and when they died, they made black holes that started out heavy. Others think that clouds of gas in the early universe could have collapsed under their own gravity, making black holes without stars at all. As these early black holes grew, they shaped the galaxies around them. Supermassive black holes might also form when smaller black holes merge together. When two galaxies come close and collide, their black holes can also join. The new black hole created by this pair is even heavier, and the process keeps repeating as the universe goes on. Today, scientists can even detect the waves that ripple through space, called gravitational waves, when two very large black holes join together. Over time, the numbers of stars and the amount of gas near the center of galaxies change. When there is more gas, the black hole can grow faster. When there is less, it grows slowly or goes quiet. The history of a supermassive black hole and how active it is depends on what is around it. If a black hole runs out of things to eat, it does not disappear. It just waits quietly until something comes near again. The effects of supermassive black holes do not stop at gravity. By pushing and pulling on the gas nearby, these black holes can help shape what kind of stars are born in their galaxy. Jets and winds from the disk around the black hole can blow gas out, stopping new stars from forming in the center for a long time. Or if the jet or wind hits a cloud of gas far away, it might shake the cloud and help start new stars forming there. Supermassive black holes can also help scientists learn about the very early universe. The light coming from around the black hole takes billions of years to reach us. When scientists look at very far away quasars and supermassive black holes, they are really looking far back in time, seeing the universe as it was when it was very young. By measuring how big and bright these black holes were in the past, and by finding out how many there are at different times, scientists learn about how galaxies and black holes formed and changed as the universe got older. The centers of many galaxies are very crowded and active places. With powerful telescopes, scientists have seen that many galaxies, even faint ones, have some sign of a supermassive black hole at their heart. Sometimes groups of galaxies together can have more than one. These giant black holes can move toward each other and eventually join, making the big black holes even bigger. There is still a lot scientists do not know. No one knows for sure if there is a limit to how big a supermassive black hole can get. Some scientists think there may be a maximum size, depending on how much matter is available and how fast the black hole can grow. Others think that if enough time passes, some supermassive black holes might keep growing larger than anything we have seen yet, especially in the centers of huge galaxies or clusters of galaxies. Even though black holes themselves cannot be seen directly, the effects of supermassive black holes are clear. In photographs using special types of telescopes, we can see circles of hot glowing gas swirling around black holes. We can also measure how the stars close to the center of a galaxy spin faster than those farther out, and how they all move under the rule of something heavy but invisible. In 2019, scientists made the first picture that showed the shadow of a supermassive black hole. They used a network of radio telescopes all around the world to act like one giant telescope. This picture showed the dark center and the bright ring of glowing gas surrounding the black hole, giving the world the first real look at the area around an event horizon. This was a picture not of the black hole itself, but of the light and matter nearby, trapped by gravity. Every galaxy that has been studied in enough detail seems to have its own supermassive black hole in the middle. The relationship between a galaxy and its black hole is very close. As the black hole grows, so does the galaxy, and the changes in one affect the other. Some scientists believe that galaxies would not be able to grow very large if not for the help of their supermassive black holes. The biggest supermassive black holes are among the most powerful objects in the known universe. When they are active, they can push out more energy in 1 second than millions of stars put together. These blasts of energy help shape the space around the galaxy and may even stop other galaxies from getting too close. They are not only important for their own galaxy, but also change the larger environment of space. Supermassive black holes connect to many different questions about stars, galaxies, and the universe. Why do they always seem to be at the center? How do they help form the galaxies we see today? What kinds of events did they cause in the early universe? These questions keep scientists searching for more evidence and making new discoveries with better tools. As technology improves, scientists continue to build new telescopes and ways to measure the light and energy near these black holes. Each discovery adds new clues. By looking at the centers of galaxies with every kind of telescope, from radio to X-ray to visible light, they learn more about how supermassive black holes live, grow, and change the universe. Supermassive black holes are some of the most surprising finds in space. Their huge mass and bright surroundings make them very special. Some, like TON 618, are so big that they stretch the limits of what we thought was possible, forcing scientists to rethink how fast and how much a black hole can grow. The oldest and farthest supermassive black holes also tell us stories about the universe when it was only a small part of its present age. By tracing how many supermassive black holes exist and how heavy they are, scientists can guess what the universe was like a long time ago and how it got to where it is now. Not all galaxies look the same, and not all supermassive black holes are the same size. Some galaxies have small black holes in their centers, only a few million times the mass of the Sun. Others, like giant elliptical galaxies, might have black holes that are tens of billions of times heavier than the Sun. The differences are shaped by the history of each galaxy. How much material was there, how many black holes joined together, and how often they were fed by gas and dust. Sometimes galaxies with supermassive black holes get close to each other. If two galaxies collide, their black holes can start to spiral toward each other too. Eventually, these black holes merge into one, sending out powerful gravitational waves and making a new, even heavier, supermassive black hole in the center of the new, larger galaxy. As supermassive black holes keep growing, they keep shaping the universe around them. Their energy, gravity, and movement help decide the size and shape of galaxies, the life and death of stars, and even the spreading of heavy elements that later form planets and new stars. With every new observation and question, supermassive black holes show how deep and rich the universe can be. Studying these cosmic giants helps understand the past, present, and future of everything in space, from the smallest particles to the biggest galaxies, all linked by gravity and time. There are many supermassive black holes in galaxies across the universe, each with its own story. One of the most interesting and massive black holes that scientists have found so far is called TON 618. This black hole is special because of its huge size and the amount of energy that comes from the space around it. To understand why TON 618 is important, it is helpful to look at how scientists discovered it and what makes it different from others. TON 618 is located very far away from Earth, in a part of the universe that is not close to our own galaxy. The light that reaches us from TON 618 comes from a time when the universe was much younger. Because light travels at a certain speed, when we look at TON 618 through telescopes, we are actually looking at how it looked billions of years ago. This helps scientists learn about what the universe was like in the past, and not just what it looks like today. Scientists did not find TON 618 by chance. They were searching the sky, looking for bright spots that did not match up with any nearby stars or regular galaxies. When they looked more closely at the light coming from this spot, they saw that it did not act like the light from a normal star. Instead, the light was much brighter and included types of light that human eyes cannot see, like ultraviolet and X-ray. To find out what was making this light, scientists used many different telescopes. Some looked for visible light, others could sense radio waves, and some were made to capture X-rays. All these tools together showed that there was something strange and powerful happening in this spot in space. By looking at how the light changed over time and what types of energy came from this area, scientists began to understand that it could only be explained by a very massive and active black hole. TON 618 stands out because the material near it shines extremely brightly. This brightness does not come from the black hole itself, but from the gas, dust, and other matter that are falling into it. As this material spirals toward the black hole, it heats up and gives off large amounts of energy. Telescopes on Earth and in space can catch this energy in the form of light and other signals. As soon as scientists noticed the brightness and the strange energy coming from TON 618, they started to study it more closely. They measured how the light changed over days, months, and years. They also looked at the motion of other objects and gas near the black hole. This helped them estimate how much mass the black hole must have in order to make these things behave the way they do. They found that TON 618 is not just large. It is one of the heaviest black holes ever found. Its mass is about 66 billion times the mass of our Sun. This number is difficult to imagine, but it helps show how much material the black hole has gathered since it was first formed. Scientists also saw that the brightness around TON 618 is much higher than most other black holes, which shows that a lot of material is falling in and giving off energy at this moment. TON 618 was also discovered because it acts as a quasar. Quasars are some of the brightest objects in the known universe. The bright light we see from a quasar does not come from the black hole alone, but from the very hot, swirling disk of gas and dust that is about to be pulled in. As this material gets hotter and moves faster, it shines with more power than all the stars in the black hole's galaxy. The discovery of TON 618 was important for scientists who want to know how big black holes can get. It also made researchers ask new questions about how a black hole could grow this large, especially in the early universe. TON 618 is a clue that some places in the universe had the right conditions for black holes to feed and grow quickly. The first steps in finding TON 618 involved scanning large areas of the sky. Scientists use surveys, which are big projects that take images or measurements of many parts of space, hoping to find rare or special objects. TON 618 appeared in one of these surveys as an unusually bright spot. Scientists then took more detailed measurements of its light. They split the light into its different colors, making a type of map called a spectrum. Different types of atoms and energy in space leave clear marks or lines in this spectrum. By looking at which lines are present and how they are shifted, scientists learn about how fast things are moving near TON 618, how hot the material is, and what kinds of atoms are in the area. The spectrum from TON 618 showed that gas was moving at very high speeds, even faster than in most other known black holes. The amount of energy released was huge, and the marks on the spectrum suggested that the region was very active, with new material falling in all the time. Because TON 618 is so far away, the light from its area has traveled for billions of years to reach Earth. This means that we are looking at something from the distant past. Scientists are seeing TON 618 as it was when the universe was much younger than today. By measuring how far away it is and how long the light has traveled, scientists can also make guesses about the age and growth of the black hole. To measure this distance, scientists use something called redshift. As the universe expands, light from faraway objects stretches to longer, redder wavelengths. The higher the redshift, the farther away and older the object is. The redshift from TON 618 is very high, which tells us that it is located at an extreme distance. This helps explain why TON 618 is so important. It helps scientists understand what the universe was like billions of years ago. When TON 618 was discovered, it quickly became a target for more research. Many scientists wanted to look at it with every type of telescope possible to gather more information. They used radio telescopes on the ground, optical telescopes for visible light, and even sent instructions to space telescopes to look at its X-rays and ultraviolet light. With each new view, they learned something more about how TON 618 works. One thing they noticed was that the center of TON 618's bright region is very small compared to its total size. This matches what is expected for a supermassive black hole. The hot, glowing disk of gas and dust is packed into a small space, spinning quickly and heating up to millions of degrees. By watching how the energy from TON 618 changes, scientists can learn about how matter flows around supermassive black holes. They can see how material disappears into the black hole, how some of it gets thrown away in powerful jets, and how the entire nearby region moves and changes over time. TON 618 has helped scientists study what happens when black holes eat matter very quickly. Some black holes do not have much to eat and are dim and quiet. Others, like TON 618, are in places with a lot of gas and dust nearby, helping them grow and shine more. By tracking how material flows into the black hole's disk and how much energy is released, scientists learn more about the process of black hole growth. The discovery of TON 618 has also given scientists a way to test their ideas about how black holes and galaxies grow together. The black hole's enormous size tells us that either it started out bigger than most, or that its galaxy had a very rich supply of matter for it to pull in over a long time. It also makes scientists wonder if even larger black holes could exist, and how common these huge objects might be in the universe. Seeing TON 618 is not only about the black hole itself. By watching the bright disk around it, scientists can measure conditions in very distant galaxies. They learn how much gas is present, how fast it moves, and what kind of environment helped this black hole grow so large. TON 618 acts as a powerful lamp, lighting up its surroundings and giving a view of space as it was billions of years ago. With each new observation, scientists get new information that helps them answer old questions but also brings up new mysteries. They track the changes in TON 618's light from year to year, noticing if it gets brighter or dimmer, or if the types of energy coming out change over time. The way scientists find and study objects like TON 618 shows how much astronomy has changed in recent decades. In the past, people looked at the sky with just their eyes or with basic telescopes. Today, they use tools that cover every kind of light, from radio waves to X-rays. Computer programs help process all this data, letting scientists find rare objects in a sky full of stars and galaxies. The story of TON 618 is ongoing. As technology changes and new telescopes are built, scientists hope to study this black hole in even more detail. There may be things about TON 618 that no one expects, and each new measurement brings them closer to understanding how the biggest black holes live and grow. TON 618 also helps scientists study extreme conditions that can never be made on Earth. The temperatures, pressures, and energies near the black hole are so high that no other place in the known universe can match them. By watching how matter behaves in these places, scientists learn about the laws of physics in ways that would not be possible anywhere else. Some of the most important questions about TON 618 have to do with its size. Scientists want to know if it is close to the biggest black hole that can ever form, or if there are even more massive ones waiting to be discovered. They also want to know what happens to matter and energy once it crosses the event horizon and disappears from view. TON 618's discovery adds to a growing list of very large black holes in faraway galaxies. Each new find helps scientists learn about the limits of how fast black holes can grow and what conditions are needed for them to reach such enormous sizes. By comparing TON 618 to other supermassive black holes, scientists are able to build a clearer picture of how black holes change over time. Some are younger, smaller, or less active, while others like TON 618 are massive and very bright. Looking at these differences is an important part of learning how galaxies and the giants at their centers have changed throughout the history of the universe. TON 618 also helps scientists figure out how energy from a single spot can affect things far away. The light from its quasar shines through clouds of gas between galaxies, changing them and helping scientists see what those clouds are made of. Every signal received from TON 618 is not just about the black hole itself, but about the pieces of the universe along the way. The discovery and study of TON 618 is a reminder that the universe is full of surprises. Every time a new object is found that breaks old records for size, brightness, or power, it shows that there is still much to learn. TON 618 is not only a scientific puzzle, but also an important tool for exploring the history and nature of space. Scientists continue to look for new ways to study TON 618. With more powerful telescopes planned for the future and better computers to analyze the vast amounts of data, they expect to uncover even more details about this enormous black hole and others like it. The story of TON 618 is not finished. Scientists still watch carefully as new data comes in, learning more about how this black hole shines, grows, and affects the world around it. Every piece of information leads to more questions about how the biggest black holes in the universe can exist and how much we still have to discover. TON 618 stands as one of the most important discoveries in the search for understanding black holes. It shows how much is possible, how much is unknown, and how far we can look into the universe's past by studying just one bright, distant point in the sky. The discovery of TON 618 changed the way people think about how big black holes can really be. To understand why TON 618 is so different, it is important to look closely at its weight and size. These are not just interesting numbers. They show how powerful, strange, and special this black hole truly is in the universe. Scientists use the word mass to talk about how much matter is in an object. Mass is not the same as size, but usually an object with more mass will also be bigger. The mass of a black hole is measured by how much material it has pulled in over its life and by how strong its gravity is. TON 618 has a mass of about 66 billion times the mass of our Sun. This makes it one of the heaviest black holes anyone has ever measured. To get a sense of what this means, scientists use the sun as a standard way to measure big things in space because the sun is already very massive. But if you took 66 billion suns and put all that matter into one single spot in space, you would have the same mass as TON 618. This amount of matter makes TON 618's gravity extremely strong, and it affects everything around it. The black hole itself is invisible, but everything close to it moves under the power of its gravity. When scientists want to figure out how heavy the black hole is, they look at several clues. They watch how gas and dust near the black hole move. The faster the gas is spinning, the more mass the black hole must have to hold it in place. If the material is moving at very high speeds, it means the gravity is strong, and so the black hole is heavy. They also look at how much energy is coming from the gas that is falling into the black hole. This material forms a disk, called an accretion disk, spinning and getting hotter as it moves in. The accretion disk of TON 618 is very bright, lighting up a huge area in space and sending out signals that can be picked up even from billions of light-years away. The amount of energy released helps scientists work backward, letting them guess how much mass is packed into the black hole's event horizon. Another clue comes from the light given off by the quasar that surrounds TON 618. The light is made not by the black hole itself, but by the superheated gas swirling around it. By measuring how this light changes and looking at the types of light produced, scientists can guess the size of the disk, and from this they can learn about the size of the black hole it surrounds. TON 618 has a very big event horizon. The event horizon is the boundary around the black hole, the point where the escape speed is faster than the speed of light. Nothing can leave once it passes this point. For TON 618, the event horizon is many times bigger than the distance from the Sun to the planets in our solar system. This makes TON 618 not just heavy but also huge in terms of the space its gravity controls. TON 618 is much heavier and larger than the black hole at the center of our own Milky Way galaxy. The supermassive black hole in our galaxy is called Sagittarius A star, and it is about 4 million times the mass of the Sun. But TON 618 is about 66 billion times the mass of the Sun. This difference is so great that TON 618 is one of the largest black holes ever measured. To be able to grow to this size, TON 618 must have had a long supply of gas, dust, and probably stars and other black holes to swallow over time. Its huge mass means it has been eating for a very long time, possibly since the early days of the universe. This also means the area around TON 618 has had very different conditions than quieter places in the universe. The light from TON 618 is so bright that, when it was first found, scientists could see it from billions of light-years away. The power comes from the disk of hot gases moving at high speeds right before falling into the event horizon. Sometimes, some of this energy is pushed outward in huge jets of particles moving almost as fast as light. These jets can reach far beyond the edge of the galaxy around TON 618. Measuring the exact size of the black hole's event horizon is hard because the black hole itself does not give off any light. Everything we know comes from watching what is happening just outside its edge. Scientists do calculations using the speed of the gas, the amount of light hitting telescopes, and models built using computers all together. These models help scientists picture what TON 618 might look like if we could see it directly. One way to understand the scale of TON 618 is to think about distances in the solar system. For example, The distance from the Sun to Neptune is about 4.5 billion kilometers. That is a huge distance. However, the span across the event horizon of TON 618 would fit inside that distance, but all the mass would be held in one small region, not spread out. Another way scientists try to describe the size and mass of TON 618 is by using gravity as a comparison. The pull of gravity near TON 618 is so strong that it would rip apart any star, planet, or even another black hole that came too close. This is why the region around TON 618 is such a bright and violent place, filled with hot gas, particles, and light created as matter rushes in toward the event horizon. Some scientists believe that black holes as massive as TON 618 are very rare. There are only a few others that may come close in weight, and each one teaches scientists more about how the biggest objects in the universe grow. The study of TON 618 makes astronomers ask if there are even bigger black holes out there, waiting to be found, or if there are limits to how big a black hole can get. All the evidence points to TON 618 being one of the largest and brightest black holes in existence. To get this big, it had to take in large amounts of material, eating faster than most black holes known. Some researchers think this could only happen early in the universe's history, when more gas and dust were nearby and could be pulled in quickly. Others wonder if TON 618 may have joined with other black holes in the past, getting bigger each time two black holes became one. When scientists look deeper, they see that the energy and material falling into TON 618 do not always fall smoothly. Sometimes the brightness changes over time, showing that the amount of material being eaten by the black hole goes up and down. Other times, the light grows stronger or weaker over months or years, telling scientists that the area near TON 618 is active and changing, not quiet. Part of measuring the mass of TON 618 comes from observing the cloud of material outside the event horizon. As the material orbits, machine measurements record its continuous movement, spinning faster and getting hotter. Over time, the measurements reveal how the black hole's gravity controls everything near it. Another piece of the puzzle is the light coming from the quasar. Every type of atom shines with its own kind of light, so when telescopes on Earth split the light into its parts, they create a map that shows which atoms are present. The way these lines are shifted also tells scientists how fast the material is moving toward or away from Earth, helping calculate how large and powerful the central black hole must be. TON 618 does more than just shine. The huge jets coming out from near the black hole blast material out into space, shaping the galaxy. These jets move so fast that they stretch, moving almost as quickly as light itself. They change the way stars and gas move and stop some new stars from forming too close to the black hole. Scientists do not know exactly where the line is between a black hole that is just very large and one that is the rare supergiant like TON 618. The more they measure black holes like TON 618, the more they learn about the limits of nature's most powerful objects. TON 618 is at a great distance from Earth, meaning the light and other signals coming from it look back in time. By measuring how far those signals have traveled using a value called redshift, scientists can work out how old the black hole is and how it has changed through the history of the universe. TON 618 is seen as it was billions of years ago, offering a window into a much earlier time. The discovery of TON 618 helps with many questions beyond just mass and size. It gives clues about how fast black holes can grow, how much matter was around in the early universe, and what happens to the galaxies that grow around giant black holes. Other black holes similar in size to TON 618 have also been studied, but TON 618 stands among the largest and most powerful. When astronomers list the heaviest black holes, the name TON 618 is always near the top. Each one that is discovered is first measured by the same methods, by the speed of nearby gas, by the amount of light being sent out, and by how much energy bursts from their centers. Some scientists use computers to model what is happening near TON 618, creating virtual pictures that show what it would look like up close. These models use the rules of gravity, heat, and motion to predict how gas moves, how light is formed, and how the black hole keeps growing. When material falls toward TON 618, not all of it ends up inside. Some gets pushed away by the growing heat and magnetic energy, blasting outward in powerful winds. These winds can carry away as much energy as a whole galaxy of stars shines in 1 year. The effect of TON 618 is seen far beyond its event horizon and even changes its whole galaxy. Measuring the mass and size of TON 618 also lets scientists think about how long it has been growing. If the black hole is already so big, it must have grown quickly after it was born, or had special conditions that let it eat faster than others. These clues help paint a picture of the universe's history. The events that happen near TON 618 are so strong, they even help scientists check if the main rules of physics always work the same way everywhere. For example, the way gravity works at TON 618's event horizon tests if famous ideas about time, light, and motion are always correct under the strongest possible conditions. TON 618's mass, event horizon, and the light from its quasar are each important data points for people who study black holes. Each new observation, measurement, or photograph adds something new to what we know and leads to more questions about what else might be possible in the universe. No one can see inside TON 618 or any black hole. Everything we know comes from the edges. But these edges hold the story of gravity, energy, motion, and time in their most powerful forms. Some astronomers keep looking for other black holes that might rival TON 618's size and mass, but only a few have been found so far. Each one teaches science about how the universe makes and grows its biggest objects. TON 618's huge event horizon, enormous mass, and incredible energy are a sign that even in a universe full of galaxies and stars, there are places where nature's power can create something far beyond everyday experience. Measuring and understanding TON 618 helps all people see the extreme limits of size, mass, and gravity. The work on TON 618 continues. Every new telescope, every better computer program, and every careful measurement adds more to the story. The study of TON 618 is a team effort, showing how scientists from around the world share their discoveries, put their data together, and find new ways to see the invisible. TON 618 will always be a subject of interest because it is so big, so bright, and so distant. Its great size and mass open the door to new ideas about what black holes can be, what rules the universe follows, and what people can learn just by looking deeply into the sky. Studying TON 618 helps everyone learn about the history of black holes and how they can reach such a massive size. The growth of this black hole did not happen quickly. Instead, it was a very long process that took place over billions of years. To understand how TON 618 became so large, scientists look at the way black holes form, the conditions around them, and the many ways in which they collect more and more mass. Most black holes begin from the collapse of a very massive star. When a star many times heavier than our Sun runs out of fuel, its core becomes unstable. Gravity pulls everything tightly together into a single small point, and a new black hole is born. But the story for TON 618 did not end when it first formed. After its beginning, it kept growing by pulling in gas, dust, stars, and even other black holes that came too close. As soon as there is a black hole, its gravity starts to attract nearby matter. This can be loose gas floating in space, clouds of dust, or full stars that pass nearby. When this matter comes close enough, it cannot escape. It is pulled toward the black hole, forming a swirling disk called an accretion disk. Inside this disk, everything spins faster and gets hotter as it moves closer to the event horizon. Some of the matter falls in and disappears forever inside the black hole, adding to the black hole's mass. TON 618 had to be in a part of space where there was a lot of material to swallow. Scientists believe that early in the life of the universe, there were great supplies of gas and dust in many places, especially near the centers of young galaxies. These clouds of matter made feeding easy for a growing black hole. Over time, TON 618 kept pulling in more and more, helping it become so large. It is likely that, as TON 618 was growing, it also met and joined with other black holes. When two black holes come close together, they can start to move around each other, pulled by each other's gravity. This process does not happen quickly. The black holes slowly spiral closer and closer, losing energy along the way in the form of gravitational waves. Finally, they join together to become one new black hole. This new black hole is heavier than both the original ones put together. This process, known as merging, can happen many times. Each time two black holes merge, the resulting black hole is heavier and can attract even more matter in the future. Scientists who study TON 618 look for clues that it might have merged with other black holes. Sometimes, the shape or movement of the matter in the accretion disk, or the gas surrounding the black hole, shows evidence of a previous crash with another black hole. Also, when black holes merge, they send out ripples through space called gravitational waves. Although astronomers cannot directly see these waves from events billions of years ago, they use their knowledge of space to guess how often these mergers happened. TON 618 might have eaten whole stars as well. In galaxies, stars move in many directions. If a star passes close enough to a black hole, the gravity can pull the star apart, spreading its gas and dust around. The pieces of the star are then pulled in, spinning into the accretion disk, and finally adding to the black hole's mass. Over billions of years, many stars in the area around TON 618 may have vanished this way. As TON 618 became bigger, its pull of gravity became even stronger. With each new piece of matter falling in, the black hole could trap things from farther away. This made it easier for the black hole to keep growing, as more matter from the galaxy center had no chance to escape. Clouds of gas, new stars, and even small black holes could all be captured and pulled in. Scientists are curious about why some black holes grow so much faster than others. TON 618 most likely had a good supply of gas and other material for a long time. In busy galaxy centers, there is a steady flow of matter moving around, making it easy for a black hole to grow. In other places where there is less gas or where stars are spread out more thinly, black holes grow slowly or stay the same size for long periods. Another way that TON 618 could have grown is by joining with black holes that came from outside its own galaxy. Sometimes galaxies move close together and merge. When that happens, any black holes in the centers of those galaxies may also come together over millions or billions of years. If this happened to TON 618, it would explain how it became so massive. By watching the light and the energy that comes from around TON 618, scientists can tell that it is still growing today. Anytime material falls into a black hole's accretion disk and shines brightly, it shows that more mass is being added. Over many years of observation, scientists have seen that TON 618's brightness can change, hinting that the eating process is still active right now. The process of pulling in new material and getting bigger is sometimes very fast and sometimes slow. If a lot of gas is close by, TON 618 can eat it quickly and shine very brightly. At other times, when there is less gas or dust nearby, growth slows down. Observing these changes helps scientists understand how feeding works for supermassive black holes. When TON 618 eats quickly, the area around it becomes even brighter. But there is a limit to how much material a black hole can eat at one time. If too much falls in, the light and energy from the accretion disk can push material away instead of letting it all be swallowed. This balance, called the Eddington limit, puts a cap on the black hole's feeding speed. TON 618 must have often been close to this feeding limit in order to become so massive. In addition to gas, dust, and stars, black holes like TON 618 can also pull in and merge with other massive black holes. Each time this happens, the result is a sudden jump in their mass. Mergers do not happen often, but when they do, they offer a big step forward in the growth of a black hole. Computer models show that to get as big as TON 618, a black hole needs a lot of time and a lot of matter close by. The universe long ago had thick clouds of gas and dust almost everywhere. That is why many of the most massive black holes are also among the oldest. They had more time and better conditions to grow. TON 618 shows signs of being from such an early time. The fact that we still see its light from far away means the black hole's growth happened very early in the universe. Its huge mass reflects how quickly it was able to pull in enough material, taking advantage of the extra gas that existed not long after the first stars and galaxies formed. Scientists believe TON 618 did not grow this big alone. Its size proves that mergers played a very important role. Even if it started as a black hole from the death of a single giant star, it would need to merge with others and swallow large amounts of gas to reach billions of times the Sun's mass. Many supermassive black holes, including TON 618, can have effects that reach far beyond their galaxy centers. As they feed and get larger, they change the way gas and stars move in the whole galaxy. When these black holes are growing quickly, they also shoot out powerful jets. These jets can send energy and material far out into space, stirring gas clouds and sometimes stopping new stars from forming close to the black hole. This means the growth of TON 618 not only shaped itself, but also changed the history of its galaxy. Another clue that helps explain TON 618's huge size is the fact that the early universe was more crowded. With less empty space between galaxies and more matter close together, it was easier for black holes to find material to feed on and to find other black holes to merge with. As the universe got older, galaxies became farther apart and had less rich gas to offer, making the growth of such big black holes harder. Mergers between black holes produce gravitational waves, tiny ripples in space that move outward in every direction. While scientists today have tools to detect these waves from nearby black hole mergers, the merging events that built TON 618 happened a very long time ago, too far and too long ago to detect directly. Still, by measuring the black hole's mass now, researchers figure out how many mergers and how much mass it had to swallow to get so big. Scientists use computer models to simulate the growth of black holes. These models show how the amount of matter available and the rate of galaxy mergers all play a role. In these models, black holes like TON 618 grow bigger by eating gas and dust continuously, and then take big steps whenever two galaxies and their black holes merge. Observing TON 618 gives scientists a live example of how black holes can keep growing. Every measurement of light, energy, or the material moving around TON 618 helps update these models, making them more accurate and better able to explain how black holes of all sizes grow over time. There are still many things scientists do not know. They wonder if there is a real limit to how big a black hole can get, or if more mergers and more feeding could create one even bigger than TON 618. They also look for clues about how often black holes collide in the early universe compared to now. Sometimes scientists see signs in other galaxies that remind them of TON 618. A bright quasar or a powerful jet may signal that another supermassive black hole is going through a similar period of growth. By comparing TON 618 to other examples, they try to build a bigger picture of black hole evolution. The path that leads to a black hole as huge as TON 618 is long and complicated. It requires many periods of eating, times of merging, and long ages spent gathering mass. The history of TON 618 is a record of much of what happened in its galaxy, and in some ways of what happened in the universe itself. No one knows for sure how many times TON 618 merged with other black holes or how much material it ate over its life. But by studying its surroundings, measuring the speed and light of its accretion disk, and using models made by computers, scientists keep adding pieces to the puzzle. They learn how TON 618 was able to become so huge, even as other black holes grew only a little or stopped growing at all. The study of TON 618's growth teaches us that black holes are not only products of dead stars, but living parts of galaxies and the universe. Their size changes over time as they eat and merge, shaping everything around them as they change. In this way, black holes like TON 618 are like engines in the centers of galaxies, always using gravity to pull in more and always changing as they grow larger. Scientists keep looking for new clues, new signals, and new measurements to help them understand how black holes grow. As more is discovered, maybe even bigger black holes like TON 618 will be found, or maybe answers about the real limits of growth will appear. For now, TON 618 stands as proof that space has had the right conditions at least once to allow a black hole to grow to an amazing size. The history of TON 618 is the story of steady, powerful, and sometimes violent growth, showing how gravity, time, and the huge forces at the heart of galaxies have shaped the universe everyone sees today. The search to understand this process continues, with TON 618 as a beacon for looking deeper into the secrets of black holes and the galaxies around them. When scientists look at TON 618, they notice not only its great mass, but also its shining light. This light is called quasar light. The light from the quasar gives scientists a way to learn much more about the black hole and its surroundings. Quasars are special objects in space. Even though the black hole itself does not shine, the matter around it gets so hot as it falls in that it makes the brightest lights in the universe. When gas, dust, or stars get close to a supermassive black hole like TON 618, they begin to spiral toward the center. This material does not fall in all at once. First, it forms a fast, hot circle around the black hole. This disk is made from gas and dust moving at very high speeds. As everything spins around, the friction between pieces creates a lot of heat. This heat becomes energy, and that is what makes the area around the black hole shine so brightly. The energy made in this way can be 1,000,000 times more powerful than the energy made by an entire galaxy full of stars. Quasars, like the one around TON 618, are among the brightest objects ever seen by anyone. Scientists can see this light from very far away, even from parts of space that are billions of light-years from Earth. Quasars help scientists measure how far away a black hole is and also let them study parts of space that are otherwise too distant to reach. The light from the quasar comes from outside the black hole. The black hole itself never lets any light escape from inside. The light and all energy are produced by the hot gas and dust moving just before it is pulled inside the event horizon. Some of this material is moving so fast that it gives off X-rays and other forms of energy that humans cannot see with their eyes. Special telescopes on Earth and in space pick up these signals, letting scientists measure everything from very bright visible light to dim radio waves and even powerful X-rays. The light from the quasar of TON 618 changes over time. When a lot of matter falls into the black hole, the quasar gets brighter. When less matter falls in, the light can become dimmer. Scientists have watched these changes by measuring the quasar's light for many years. This helps them find out when the black hole is eating new material and how quickly it is growing. Because quasars are so bright, they become markers for finding the farthest and most powerful black holes. Many of the black holes discovered in other galaxies were first seen because their quasars shined brighter than everything else around them. TON 618 was also found in this way. Its quasar stood out in the sky as an unusually bright spot among many dimmer stars and galaxies. Quasars also produce energy in other ways. Sometimes, not all the gas and dust that falls toward TON 618 gets swallowed up. Instead, part of it is blown out in thin jets that move almost as fast as light. These jets can travel far beyond the center of the galaxy. When scientists look at the radio waves coming from TON 618, they sometimes see these jets pushing through space. They can be longer than the whole galaxy itself. Jets help carry energy away from the black hole and can change the way the galaxy around it grows. When the jets from a black hole move through space, they hit clouds of gas and dust. This can heat up these clouds and sometimes make them glow. As the jets pass through, they can push material far away, changing how stars are born in the areas they pass. TON 618's jets may have helped shape the path of its whole galaxy, stopping some stars from forming and helping others to grow by stirring the gas and dust. The energy coming from the quasar and jets also carries information about the black hole. By studying the color and strength of the light, scientists find clues about the temperature, movement, and even the types of atoms found near TON 618. For example, some types of light can only be made by very hot gas, so when that light appears in the spectrum, scientists know the temperature near the event horizon is extremely high. A quasar's light has to travel through much of the universe before reaching Earth. As it goes, it passes through clouds of gas and dust that float between galaxies. Each time the light moves through one of these clouds, some colors of the light are blocked, while others pass through. When the light finally reaches Earth, it carries a record of all the clouds and material it passed along the way. By looking at small changes in the light's spectrum, astronomers learn not just about TON 618, but also about everything between here and there. The spectrum of the quasar's light is like a fingerprint. Every atom leaves its mark by either absorbing or giving off certain kinds of light. By collecting the light from TON 618 and splitting it into its different colors, scientists make a detailed map that shows what happened as the light traveled through space and also gives a close-up look at the area just outside the black hole. Quasars, like the one around TON 618, show that the area around a black hole is not dark and empty. It is full of swirling matter, powerful forces, and extreme energy. The light we see from a quasar can change quickly or slowly. Sometimes explosions of energy light up the area as new material falls in. At other times, the brightness drops when less material is available. Because TON 618 is so far away, the light from its quasar has traveled for billions of years to reach Earth. This means that when scientists study TON 618's quasar, they are looking at a very ancient part of the universe. The light shows how things were at that time, giving a picture of the universe long ago. By looking at many quasars, scientists build up a timeline that helps explain how galaxies and black holes changed as the universe got older. Sometimes the quasar around TON 618 can outshine the entire galaxy. This happens when the accretion disk is very active, with a lot of new gas and dust falling in. The huge brightness can be seen with powerful telescopes, even from very far away. This is why TON 618's quasar first attracted the attention of scientists searching the distant sky. The light from the quasar does not only tell about the black hole, it also tells about the space and galaxies between TON 618 and Earth. As the light makes its journey, every cloud or piece of matter it passes through changes it just a little. Scientists read these changes to learn what the universe was made of billions of years ago and how that has changed over time. Not all material that heads toward a black hole ends up falling in right away. Some of it swirls in the accretion disk for millions of years before finally being swallowed or pushed away by jets. The competition between falling into the black hole and being thrown outward creates the changing, glowing pattern that scientists see as the quasar's light. Quasars are so powerful that they can sometimes change the whole galaxy. The energy coming from the jets and the glowing disk can heat up gas far away, which may slow down the making of new stars. The details of how this happens are still being studied, but many scientists believe that very powerful quasars, like the one around TON 618, have had a big effect on the shape and history of whole galaxies. Sometimes the quasar light from TON 618 seems to flicker or change over time. This flickering tells scientists about the way matter is moving and changing near the black hole. For example, if the brightness of the quasar goes up and down quickly, it can mean the accretion disk is unstable, or that new pieces of gas or stars are being added suddenly. Careful watching of these changes helps astronomers learn about the everyday life of black holes. Scientists also use quasar light to test some of the most basic facts about the universe. Because the light from quasars travels such a huge distance, any change in the laws of nature would also change the light. So far, the studies of quasar light show that the laws of physics have stayed the same for billions of years. Astronomers also find that the quasar light from TON 618 has been stretched out as it moved through the expanding universe. This stretching is called redshift. The higher the redshift, the farther and older the object is. TON 618 has a very high redshift, meaning its light left the area around the black hole when the universe was young. When this happens, the brightest and hottest parts of the quasar are seen at longer, redder wavelengths. Choosing to study the light from quasars is very important because light is one of the only ways to learn about faraway black holes. Since the black hole itself can never be seen directly, scientists learn everything by watching what happens to the matter and light outside the event horizon. TON 618 is one of the best examples of how studying a quasar teaches scientists about black holes. Each new measurement, whether it is of brightness, color, change over time, or movement of the jets, adds to what is known about TON 618 and others like it. When the next generation of even more powerful telescopes begins taking data, they will be able to see the quasar of TON 618 in even greater detail. This will show how matter moves, heats up, and changes as it falls toward the black hole, and how the biggest black holes affect everything around them. The quasar around TON 618 keeps giving information about both what is very close to the black hole and what is far away between the black hole and Earth. It is like a bright light shining through the whole universe, carrying information over many billion years. The strong light and other types of energy from TON 618's quasar also help explain why there are not more supermassive black holes growing just as fast today. The energy coming from these quasars can push gas out of galaxies, slowing down the creation of new stars and stopping other black holes from becoming very large. In this way, powerful quasars help set the pace for how galaxies and their black holes grow and change. Astronomers will keep studying the light from TON 618's quasar for many years. Every new discovery shows more about how matter and energy behave in the most extreme conditions in the universe. The brightest quasars, like TON 618, are more than just beautiful. They are treasures for science, carrying clues about the biggest questions in space. The next steps in learning from TON 618 will come as scientists use new tools and as more quasars are found and compared. The light from TON 618 is not only the sign of a huge and powerful black hole, it is also a tool that lets people on Earth look back in time, up close to the most mysterious things in the universe. The ongoing study of these bright lights is helping solve the great puzzles of black holes, galaxies, and the universe itself. Learning from the light of TON 618 teaches much about black holes and the universe, but those discoveries are only possible because of special scientific tools. Scientists have created many different kinds of instruments to explore space and understand black holes like TON 618. Each tool lets them observe something different, and together they let people see clearly what happens even in distant, hidden, or strange places in the universe. One important tool is the telescope. Telescopes are used to collect light from objects that are far away. Some telescopes are built on high mountains or in dry deserts on Earth, while others are sent out into space. By being far from cities, high on mountains, or above Earth's atmosphere, telescopes can get a better view of the night sky with less light pollution and no clouds getting in the way. There is not just one kind of light. The light that people can see with their eyes is called visible light, but many signals in the universe are invisible to human eyes. Scientists have built telescopes that can collect different types of invisible light, like radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each of these types of light is made by different events and kinds of energy in space. For a black hole like TON 618, radio waves can show scientists the shape and strength of jets coming from the area near the black hole. Infrared lets astronomers observe dust that is heated by the black hole's activity. Ultraviolet and X-rays are important because very hot gas around the black hole shines in these types of energy. Gamma rays mark the most powerful and rare events, like short bursts from matter being thrown out at very high speed. One well-known space telescope for visible light is named Hubble. It has helped scientists photograph galaxies and bright quasars in great detail. Other telescopes like the Chandra X-ray Observatory focus on X-rays, and the Very Large Array in New Mexico looks at radio signals. All around the world and in space, these instruments work together, sometimes looking at the same object at the same time. To study TON 618, scientists point all these different telescopes at the right place in the sky. Each telescope collects its own kind of light, sending back data to computers and researchers. Combining this data, scientists can produce a complete picture of the black hole's surroundings. They see the glowing accretion disk, the jets, the hot gas, and the radiation coming from the quasar. With each kind of light, they find new clues. Not every signal is easy to catch. The faintest radio waves from TON 618 travel billions of years to reach Earth. Sensitive radio telescopes must be tuned carefully to find these small signals. For very distant sources, such as TON 618, the signals are much weaker and sometimes drowned out by noise. Scientists need to use the largest dishes or arrays of many antennas working together. These arrays can stretch over many kilometers, making them act like a single, much larger instrument. Infrared light is also useful, but it is easily blocked by water vapor and dust in Earth's atmosphere. To avoid this problem, telescopes for infrared light are often put on high mountains, in deserts, or launched into space on satellites. These special locations make the technology able to see the warm dust and material around TON 618, which would otherwise not be visible at all. X-ray telescopes are always put outside our planet because Earth's atmosphere blocks X-rays from space. These telescopes show where the hottest, fastest-moving material is before falling into the black hole. By detecting X-rays, scientists know where the energy is highest and how matter is behaving very close to the event horizon. In addition to light, scientists use another kind of signal to watch black holes. These are called gravitational waves. Gravitational waves are not light or sound. They are gentle ripples in the fabric of space, made when massive objects like black holes join together. On Earth, scientists build giant detectors like LIGO and Virgo to watch for these tiny waves. The waves stretch and squeeze space by the smallest amount, and it takes very precise machines to notice the change. When two black holes merge, they create a burst of gravitational waves. Scientists have seen waves from joining smaller black holes and from neutron stars, but the merging of huge, supermassive black holes like TON 618 may be too far and happened too long ago for current detectors to capture. New detectors are being planned and built, so in the future scientists may be able to detect signals from much farther away and even from more massive black holes. Computers are as important as telescopes. Every time a telescope collects data, it gathers so much information that people cannot look at it all by hand. Computers sort through light signals, look for patterns, match up data from different telescopes, and make the images scientists use for studying. Without computers, it would be almost impossible to make sense of all the details hidden in faint light from billions of years away. Computer models and simulations are tools that allow scientists to experiment with black holes. Since we cannot travel to TON 618 or see inside a black hole, scientists write equations describing how matter, energy, and gravity work. Then they use powerful computers to create a virtual version of a black hole. They can change how fast the black hole grows, how much material is nearby, or what happens when black holes merge. The models show what would be seen if those things happened in real life. These simulations are tested against what is really seen through telescopes. If a simulation gives results that match what the telescopes find, scientists know their ideas are likely correct. If not, they change the model and try again. This back-and-forth process helps scientists slowly learn more about things no one can touch or see up close. When a quasar like TON 618 is studied, astronomers take a special kind of measurement called a spectrum. By spreading out the light into all its different colors or energy levels, they find lines made by different atoms and molecules. Each line tells about the speed, temperature, and movement of the gas close to the black hole. This information, together with computer models, lets astronomers estimate how much the black hole weighs, how big it is, and how it is changing. There are other creative methods. Sometimes when a black hole passes exactly in front of a more distant star or galaxy, its gravity bends the light. This is called gravitational lensing. The black hole acts like a lens, making the light from the other object appear brighter or bent in a way that would not happen without the black hole being there. By measuring how much the light bends and brightens, astronomers can measure the mass of the black hole causing the lens effect. Black holes themselves cannot be seen, but because they affect things around them, the movement of nearby stars and gas is watched carefully. If a star is seen moving quickly around an invisible point in space, or if gas swirls faster the closer it gets to that spot, scientists can tell that a black hole must be there. With all these tools, telescopes, computers, detectors, and models, scientists keep looking for more black holes and learning more about the ones they already know. Each discovery is shared with researchers everywhere, and often teams from different countries use their instruments together, watching the same object together for months or years. Sharing information is very important. A single scientist or a single telescope might miss something, but when groups work as teams, or many telescopes are pointed at the same place, new discoveries are made. Special networks like the Event Horizon Telescope connect many radio dishes all over the world. This network makes one huge, Earth-sized, virtual telescope, able to take fine pictures of the area around a black hole's event horizon. These tools have created the first images of the bright area near a black hole, and one day may help make better pictures of TON 618. By working together, telescopes can make images not just in visible light, but in radio, X-ray, and other forms, building a full view of the black hole's surroundings. Large databases are built so astronomers can compare data from different years, looking for changes in brightness, new jets, or special events happening near TON 618. Each new piece of data adds to the knowledge, letting scientists look for patterns or special signals that could mean something new or strange is happening. Education and practice are part of using these tools well. Scientists spend years learning how to use telescopes, how to design computer models, and how to understand the patterns in complex data. They also teach students and new scientists so that each new group is ready to use the next generation of tools. New telescopes and detectors are being planned. Some will be put in space so they can take clearer pictures without the blur of Earth's air. Others will use many antennas spread across whole continents to capture faint radio waves. There is work to be done on gravitational wave detectors as well. New kinds will try to catch signals from even larger and more distant black holes than before. Every scientific tool has limits. Some can only see one type of light. Some must wait for just the right moment to look at a black hole or its quasar. But because astronomers use many tools together, they can answer questions that are too hard for just one telescope by itself. As technology changes, new discoveries become possible. The data collected now may help plan the next telescope, and each new image or wave from TON 618 can change what scientists expect from the universe. Surprises are always possible when a new tool makes it possible to look in a new way at a new part of the sky or with new details never seen before. In all of these discoveries, the story of TON 618 and similar black holes is being built piece by piece. Every tool, every observation, every model, and every detector has a role in making the invisible universe more clear. Working together, scientists and their instruments uncover the secrets of black holes, learning how they grow, how they shine, and how they change the galaxies around them. People everywhere can learn from these discoveries. Sometimes even basic science classes talk about black holes and show pictures made by these telescopes and tools. The tools built to study TON 618 will help discover new black holes, new phenomena, or new details about gravity and energy. Every time an instrument is improved or a new signal is seen, there is a chance to understand something no one has ever known before. The search using all these tools is not only about TON 618. It is about discovering the universe, and every tool is a new way to look at nature's biggest and most mysterious places. As more data comes in, as computers get faster, and as telescopes see farther, the picture of black holes and their role in the creation and life of galaxies will become more complete, and humans will know more about where they are in the universe. With every discovery, the understanding of black holes grows deeper, but there are still many mysteries left. TON 618 is one of the greatest mysteries in the universe because it is so large and bright, and because it challenges what is known about the way black holes work. This supermassive black hole raises new questions about how the universe makes such giant objects and how they change the galaxies around them. Even after studying TON 618 with powerful telescopes, computers, and scientific teamwork, there are many things that remain unknown. Scientists know TON 618 is one of the heaviest black holes ever seen. Its mass is about 66 billion times the mass of the Sun. It shines with a light that is brighter than nearly any other object in the universe, and the signals from its quasar reach across billions of light years. But there are still questions about how it grew to be so enormous, how many like it exist, and what the limits of black holes might be. One of the biggest questions is whether there is a maximum size for black holes. Some scientists believe the universe must have a rule that stops black holes from growing forever. Others think there might be black holes even bigger than TON 618 somewhere far out in space, just waiting to be found. To answer this, scientists keep searching the sky for other bright quasars and looking for signals from places they have never seen before. Every improved telescope, every new detector, and every careful study may bring the discovery of something even larger or more surprising. TON 618 helps test the rules of physics. Strong gravity is not only powerful, it is also a way to check if the basic laws of nature always work the same way. When scientists look at the light from TON 618, they see how energy, matter, and gravity all come together in a way that does not happen anywhere else. This helps scientists decide which ideas about black holes are correct and which need to be changed or improved. Many scientists wonder how TON 618 found so much material to swallow. The black hole must have grown by pulling in huge amounts of gas and dust and maybe even merging with other big black holes. Some of these events may have happened long ago, when the universe was young. The ancient light seen from TON 618 helps tell a story about how the universe looked billions of years ago. When scientists try to follow TON 618's growth, they use computer models. These models add up all the ways a black hole can get heavier, by eating gas, collecting new dust, swallowing stars, or even joining other black holes. The results often surprise scientists, sometimes showing that a black hole could grow much faster than expected under the right conditions. Other models say there should be a limit, and that TON 618 might be near the largest possible black hole that can exist. Finding answers is not easy because there are problems that only appear when studying such big and powerful objects. The biggest black holes give off so much energy that they can push material away, slowing their own feeding. This is called feedback. When too much energy comes out, new gas can be blown away or heated up so it cannot fall into the black hole. Feedback may set a limit, but it is still not clear how this rule works in every part of the universe. There is also mystery in the way TON 618 affects its galaxy. Supermassive black holes, like TON 618, can make powerful jets that move far into the galaxy or even outside it. These jets heat gas, change the motion of dust, and can slow down or speed up the birth of new stars. Scientists do not know exactly how much power TON 618's jets have, or exactly how they change the galaxy over millions or billions of years. Some black holes, even if they are as big as TON 618, are almost invisible. They may be quiet, with little matter falling in. Without a bright quasar, these black holes cannot be seen with current tools. Scientists are building new instruments to find these hidden giants. In the future, these tools might show that there are many more supermassive black holes waiting to be discovered. There is also the question about the very beginning of the universe. Scientists want to know how the first black holes formed. Some say the first ones were created when massive clouds of gas collapsed, even before the first stars. Others think the earliest black holes began as the leftovers from the very first, very largest stars. The history of TON 618 could help answer which idea is correct. The light from TON 618 has traveled across space for billions of years. As it moves, the universe changes. The material TON 618 swallowed, the energy it sent out, and the way it slowed or shaped starbirth have all affected the history of the galaxy around it. In this way, the story of TON 618 is also the story of many galaxies, how matter, energy, and time come together to make the universe everyone sees today. All black holes, not just TON 618, are laboratories for learning about space, time, light, and gravity. They are important for understanding what the universe is made of. They help scientists think about what happens to matter when it is squeezed as tightly as possible, and about the edges of physics where normal rules begin to break down. Many tools have been built for this search, and new ones are coming. With each new generation of telescopes, humanity can look farther away, find fainter objects, and see new kinds of energy. Large computers are used to make sense of the mountains of data from observatories. Scientists in many countries work together to share what they find with everyone. Each piece of the puzzle brings people closer to answering the biggest questions about space. The discovery of TON 618 and other black holes like it shows how much is left to explore. Space is full of unanswered mysteries. There could be black holes larger than anyone has ever found. There might be rules that nobody has guessed yet that decide how galaxies and black holes change over billions of years. The more that is learned, the more new questions come up. Supermassive black holes challenge what everyone knows about space. The size of TON 618 tells about limits in the universe. The light from its quasar gives information about how energy moves and how matter acts under the strongest pull of gravity. Even the way TON 618 changes or grows tells about time and change through the history of everything. Although TON 618 is very far away, it connects to Earth and to all people. By looking at TON 618, scientists are also looking back in time to the early days of the universe. Every discovery made about TON 618 helps teach about how galaxies grow, die, and change. It teaches about where the elements in the universe come from and about how stars form and end their lives. Sometimes the study of TON 618 and other black holes leads to surprises. A scientific idea may be challenged, or a new kind of signal might be found. Each observation can open a new door. These surprises are important because they show how every answer brings more understanding, but they also show how much more there is to learn. The future of studying black holes is bright. New telescopes that will see farther than any built before are already being planned and built. Teams of scientists prepare to look for new black holes, bigger black holes, and for clues that will help decide what the true limits are. Computer models grow stronger and more detailed, and the sharing of knowledge among countries and groups is making science faster and more open. TON 618 will always be important, even as new discoveries are made. Its mass and brightness make it a clear target for many types of research. Whether it stands as the largest black hole ever or only one of the largest, it will keep teaching scientists about the big rules of the universe for a long time. There is always a chance there could be a surprise. Astronomers might find a black hole larger and more powerful than TON 618, or they might find that TON 618 is special, shaped by events that happened only once or a few times in all of history. The ongoing search for more black holes and for better understanding of those already known means that the story of black holes is still being written. When people look at the stars, or when young students hear about black holes in school, they are connecting to the long story of exploring space. TON 618 becomes part of this story. Its discovery reminds everyone that even with so much already learned, the universe is full of things that are mysterious, powerful, and waiting to be understood. Scientists keep asking questions about TON 618. They want to know if it is still growing or if it has reached its biggest possible size. They watch its brightness, its jets, and its effect on the galaxy around it for any signs of new change. Every year, by gathering new data, building stronger telescopes, and creating better computer models, they move one step closer to understanding fully how the universe's most massive objects can exist. The search for answers brings people together. Scientists in many countries work as teams, sharing their discoveries, their ideas, and their hopes that some of the biggest mysteries will one day be solved. TON 618 is an example of what can be learned through patience, care, and working together. The mystery of TON 618 is also important for thinking about the future. What will humans discover as they push the limits of knowledge? What answers will come from looking deeper and farther than anyone before? The universe is wide and full of secrets, and every black hole found, every signal measured, adds one more piece to the puzzle. TON 618 stands at the edge of what is known and what is still to be discovered. It is an invitation to keep exploring, keep wondering, and keep building new ways to learn. The journey to understand black holes, from the smallest to the largest, is one of the most exciting parts of science. Black holes like TON 618 are more than just strange points in space. They are a sign that the universe is always growing, always changing, and always full of possibilities. From TON 618's first light to the newest discoveries, the lesson is always the same. The more people look, the more there is to find. Studying TON 618 touches every big question about space, time, matter, and energy. It shows how everything is connected and how every discovery brings humans closer to seeing the universe as it really is. And as new discoveries are made, the mystery at the heart of TON 618 keeps inspiring curiosity, hope, and a never-ending search for knowledge.